The universe's ultimate power source is not a star but a black hole. This is not a science fiction fantasy, but a direct prediction of Einstein's theory of gravity. We are going to explore how a region of infinite gravitational pull could be transformed into a cosmic power plant. By the end, you will understand the profound physics that could one day allow a civilization to harvest energy from a spinning black hole. The principles are real, involving warped space, negative energy, and a process that sounds like magic. How could anything escape a black hole's grip to give us power? And what would it take to build such an engine? What does it say about us that we can even conceive of tapping into such a force? This paradox begins to unravel when we stop thinking of a black hole as a simple hole. It is more accurately described as an object, a region of space defined by its immense mass and gravity. And according to Einstein's most famous equation, mass and energy are two sides of the same coin. The colossal mass of a black hole represents a staggering reservoir of energy locked away by gravity. But there is a crucial distinction to make. Not all of that energy is permanently lost behind the event horizon, the point of no return. A significant portion can exist outside, swirling in the very fabric of space itself. This is especially true for a black hole that is spinning, which is almost every black hole we believe exists. When a black hole rotates, it does not just drag matter around it, it drags space-time. The region around the black hole, called the ergosphere, is forced to rotate along with it. Think of it like being caught in a powerful whirlpool. The water closest to the center spins the fastest, pulling everything along for the ride. The ergosphere is that whirlpool, but made of space and time. Within this twisted region, something extraordinary becomes possible. An object can enter the ergosphere, and if it is cleverly maneuvered, it can escape again. It is not falling into the black hole, but it is being whipped around by the tornado of spinning space-time. This rotation is pure energy, a kinetic fury embedded into the universe's structure by the black hole's spin. This energy is not the black hole's mass. It is not the slow, theoretical trickle of Hawking radiation. It is not even the violent light show from matter crashing into an accretion disk. This is the black hole's own rotational energy, a vast and accessible reservoir swirling just outside the point of no return. The key to a cosmic power plant lies not in mining the black hole's heart, but in tapping the immense spin of its outer storm. This theoretical whirlpool holds the key to a power source of almost unimaginable scale. In 1969, physicist Roger Penrose proposed a mechanism to steal that energy, a thought experiment so elegant it bears his name. The Penrose process begins with an object, perhaps a spacecraft or a large chunk of matter, venturing into the ergosphere. Here, the laws of physics permit a strange transaction. The object is designed to split apart. One fragment is deliberately sent plunging into the black hole, but with a crucial twist. It is fired in a direction opposite to the black hole's rotation, like throwing a rock backwards against a raging river current. In the ergosphere's warped physics, this fragment can actually carry what is called negative energy. It is not negative in a mystical sense, but in a precise gravitational accounting. By falling in against the spin, it reduces the black hole's total rotational energy. The other fragment, now unburdened, gets catapulted out of the ergosphere with more kinetic energy than the original whole object had when it entered. Think of it not as creating energy from nothing, but as a cosmic version of a gravitational slingshot. A spacecraft uses a planet's gravity to gain speed, stealing a tiny bit of the planet's orbital momentum. In the Penrose process, the fragment escaping is like that spacecraft, and the black hole's spin is the planet. The fragment that falls in is the price paid, the ballast dropped to allow the escape. The black hole itself pays the bill, its furious spin slowing down by a minuscule amount. With each cycle, energy is transferred from the black hole's rotation to the escaping matter. A civilization could, in theory, collect these high-velocity fragments and convert their motion into usable power. It is a direct withdrawal from the universe's most formidable bank account. But this raises a pressing, practical question. How could we possibly engineer such a delicate and violent transaction in reality? The Penrose process gives us the theoretical playbook, but to build the machine we need the actual blueprints. These blueprints were drawn not by an engineer, but by a mathematician named Roger Kerr. In 1963, Kerr solved Einstein's immensely complex field equations for a rotating black hole. His solution, known as the Kerr metric, is the precise mathematical description of how space and time warp around a spinning cosmic giant. It is the instruction manual for the universe's most powerful dynamo. This metric reveals 3 critical zones, each with a distinct role in our energy harvesting scheme. The first is the event horizon, the ultimate point of no return. For a spinning black hole, this horizon is not a perfect sphere but is squashed at the poles and bulging at the equator, shaped by the relentless spin. Nothing that crosses this boundary, not even light, can ever communicate with the outside universe again. But just outside this horizon lies the second and most important zone, the ergosphere. The Kerr metric defines its outer boundary as the static limit. This is not a physical barrier, but a surface where the drag of spinning spacetime becomes so powerful that it is impossible to stand still. To resist being swept along, you would have to move faster than light itself, which is impossible. Inside the ergosphere, everything, including the fabric of space, is forced to rotate with the black hole. This is the phenomenon of frame dragging, where the black hole's rotation literally twists the coordinate grid of the universe around it. The ergosphere is not empty. It is a maelstrom of pure rotational energy, a kinetic reservoir created by the warping of spacetime itself. This is the active region for the Penrose process. It is where our theoretical object enters, splits, and allows one piece to be flung outward with amplified energy. The third feature defined by Kerr's math is the singularity at the very center. But for our purposes, the singularity is irrelevant. We are not trying to reach the heart of the black hole. We are farmers, not miners, and we are interested solely in the fertile land just outside the event horizon. The Kerr metric makes one thing abundantly clear: without spin, none of this works. A non-rotating black hole, described by an older solution, has a spherical event horizon and no ergosphere. There is no swirling vortex of spacetime to tap into, no frame dragging to exploit. Rotation is the essential ingredient. It transforms a simple gravity well into a complex, dynamic engine. It provides the leverage needed to extract energy from a region of otherwise inescapable gravity. So when we speak of harvesting infinite energy, we are speaking specifically of a Kerr black hole, a spinning monument to Einstein's theory where space, time, and energy are woven into a single harvestable storm. This bizarre concept of negative energy is the true fuel for our cosmic power plant. To understand it, we need to shift our perspective entirely. In the normal world far from a black hole, energy is a positive quantity. A rock at rest has energy from its mass. Throw it and it gains kinetic energy. All of this is positive, measured from our stationary viewpoint in the distant universe. But within the ergosphere, the rules of the game change because spacetime itself is moving. The black hole's spin drags the coordinate grid around it like a rushing river. An object sitting still in that river, from our distant perspective, is actually being carried along at tremendous speed. Its total energy, from our point of view, is a combination of its mass energy and this hidden kinetic energy from the dragged spacetime. Now imagine that object is cleverly broken apart. One piece is fired directly against the current of this spacetime river, deep into the ergosphere and toward the event horizon. Because it is moving opposite to the relentless drag, its motion relative to the swirling space can result in a total energy value that, from our distant viewpoint, is less than zero. This is what physicists mean by a negative energy orbit. The fragment itself is made of normal matter, but its situation in the warped geometry gives it this accounting anomaly. It possesses negative energy relative to us, the observers, at infinity. When this negative energy fragment crosses the event horizon and is lost forever, it performs the critical transaction. The black hole absorbs it, and because the fragment's energy ledger shows a negative entry, the black hole's balance sheet must adjust. Its total mass and, more importantly, its rotational energy decrease. The black hole literally loses a tiny bit of its spin. That lost rotational energy does not vanish. It has been transferred by the precise mechanics of the split to the other fragment that escaped. That escaping piece rockets away with more energy than the original whole object carried in. We have not created energy. We have simply moved it from one column in the universe's ledger to another, converting the black hole's furious spin into a tangible, collectible burst of kinetic energy. The process is a gravitational form of energy laundering, using the bizarre rules of warped spacetime to transform an inaccessible spin into a usable resource. Each successful cycle slows the black hole down by an infinitesimal amount. For a supermassive black hole with the mass of millions of suns, its rotational energy is so vast that this harvesting could, in principle, continue for eons, providing a civilization with power on a scale that dwarfs all the stars in a galaxy. Yet this still feels like a thought experiment, a physicist's elegant trick. Can such a delicate quantum transaction be scaled up to power a city, or even a starship? The particle splitting of the Penrose process is a powerful idea, but it presents an immense engineering challenge. How do you precisely split and aim matter in the most violent environment imaginable? Nature, however, offers a more elegant and potentially more powerful alternative, one that works not with chunks of matter, but with pure waves of energy. This is the phenomenon of superradiant scattering, the wave analog to the mechanical Penrose process. If the Penrose process is like dropping a precisely weighted bucket into a whirlpool to sling water out, superradiance is like whispering into that whirlpool and having your whisper come back as a shout. The principle revolves around any wave, be it electromagnetic like light or gravitational ripples in spacetime itself, approaching a spinning black hole. When such a wave enters the ergosphere, the same twisted region of dragged spacetime, something remarkable happens. Part of the wave can be scattered in such a way that it gains energy directly from the black hole's rotation. The wave essentially steals a tiny bit of the spin, amplifying itself in the process. A simple analogy can be found in everyday sound. Imagine a police siren on a moving car. As the car races toward you, the sound waves are compressed, their frequency increased, and the siren sounds higher in pitch. This is the Doppler effect. Now think of a wave approaching our rotating black hole. The swirling spacetime in the ergosphere acts like a moving medium. If the wave's frequency is just right, lower than the rotation rate of the black hole, the scattering process can act like a cosmic version of that siren effect, but in reverse and with amplified power. The wave scatters off the black hole's gravitational field, not with a loss but with a gain. It leaves the encounter with more energy than it arrived with, while the black hole's rotational speed decreases correspondingly. This is not a one-time particle event. It is a continuous, scalable process. A steady stream of low-frequency radiation directed at the black hole could, in theory, be reflected back as a more powerful beam. The black hole itself becomes an amplifier, converting its immense rotational energy into a focused output of electromagnetic or gravitational waves. The efficiency here is the key difference. While the Penrose process requires precise ballistic maneuvers with matter, superradiance works with ethereal waves that are far easier to manipulate at a distance. You would not need to send fragile machinery into the ergosphere. You could simply set up a mirror or a series of mirrors in a vast orbit around the black hole. Aim your input beam at the ergosphere and collect the amplified output beam as it reflects back. It transforms the concept from a risky mining operation into something resembling a stationary power station, with the black hole as its roaring, energetic core. This continuous extraction paints a staggering picture of a future civilization's power grid, one anchored not to stars but to the silent, spinning giants at the hearts of galaxies. Yet, even this elegant wave-based method confronts a fundamental barrier, one that defines the very nature of a black hole and seems to forbid any escape. But if a wave can be amplified by scattering off the ergosphere, what happens if we never let it leave? This is the mind-bending leap that transforms a simple amplifier into a runaway reactor, a concept known as the black hole bomb. The idea was first explored by physicists William Press, Saul Teukolsky, and others in the early 1970s. They asked a simple yet profound question. What if you placed a giant spherical mirror around the black hole just outside the ergosphere? Now consider a single photon of light or a ripple of gravitational wave generated inside this mirrored cavity. It travels inward, enters the ergosphere, and undergoes superradiant scattering. It gains energy from the black hole's spin and is reflected back out, only to hit the surrounding mirror. The mirror bounces it back toward the black hole, where the process repeats. Each pass through the ergosphere steals more rotational energy, amplifying the wave's power. Trapped inside this perfect reflective shell, the wave cannot escape. It simply bounces back and forth, growing exponentially stronger with every trip through the black hole's energetic whirlpool. This creates a runaway feedback loop, like a microphone placed too close to a speaker. A tiny whisper enters the microphone, is amplified out of the speaker, only to be picked up again and made louder, resulting in an ear-splitting screech of feedback. In the black hole bomb, the microphone is the superradiant scattering process, the speaker is the amplifying black hole, and the mirror ensures the signal keeps circulating. The energy inside the cavity would skyrocket. The trapped radiation would build up to such incredible intensities that the pressure would become astronomical. Eventually, the mirror itself, no matter how strong we imagine it to be, would shatter. The pent-up energy would be released in a single, catastrophic burst, a detonation of pure spacetime energy that could outshine a supernova. This is the black hole bomb, not a weapon in the traditional sense, but a description of the maximum possible energy extraction process. It represents the theoretical upper limit of efficiency. An engineered version would not let the energy build to the point of explosion. Instead, we would design a semi-permeable mirror or a series of collectors that carefully bleed off the amplified energy at a controlled, sustainable rate. In this configuration, the black hole bomb model becomes the blueprint for the ultimate engine. The black hole's spin is the fuel, the superradiant process is the combustion, and the mirrored containment system is the reactor chamber. This engine would not burn chemical fuel or split atoms. It would directly convert the rotational momentum of a fundamental spacetime object into a torrent of usable power. The scale is almost incomprehensible. A single, properly harnessed supermassive black hole could, in principle, provide energy for cosmological timescales, powering not just a civilization, but the activities of a civilization so advanced its energy needs would dwarf our own. It shifts the question from "is it possible?" to what kind of universe do we build when energy is no longer a limiting factor, but an infinite canvas? Building a mirror that can contain such fury is the first great engineering nightmare. A physical shell, even one constructed from a hypothetical perfect material, faces two insurmountable problems. The first is the sheer, incomprehensible scale. To surround a supermassive black hole, this mirror would need to be an astronomical structure, a rigid sphere larger than our entire solar system. The second, more fundamental problem is stress. The amplified radiation inside would exert unimaginable outward pressure, while the black hole's gravity would pull inward with equal ferocity. Any known or conceivable solid material would be instantly pulverized by these opposing cosmic forces. A physical mirror is a fantasy, so we must think not in terms of steel and glass, but in terms of forces and fields. We must engineer a mirror made not of matter, but of the black hole's own environment. One speculative possibility lies in exploiting the black hole's intense magnetic fields. Many black holes, especially those actively feeding, are surrounded by swirling disks of hot plasma. This charged, chaotic soup can generate magnetic fields of staggering power, fields that are twisted into coils and loops by the black hole's spin. These magnetic structures could, in theory, act as a kind of natural containment field. Charged particles and even electromagnetic waves can be reflected or channeled by powerful magnetic barriers. A sufficiently advanced civilization might learn to manipulate and stabilize these innate magnetic fields, sculpting them into a persistent, dynamic shell around the ergosphere. This magnetic bottle would not be a perfect mirror, but it could serve as a semi-permeable barrier, allowing a controlled stream of input radiation in and a torrent of amplified energy out, all while containing the runaway feedback at its core. An even more exotic proposal involves the black hole's own gravity. The intense curvature of spacetime just outside the ergosphere creates what is known as a photon sphere, a region where gravity is so strong that light itself can orbit the black hole. This is not a stable orbit, but it suggests a principle. Could we engineer a gravitational lensing array, a ring of massive objects placed in precise orbits, to bend the escaping amplified radiation back toward the black hole? This would create a gravitational mirror using the warping of spacetime itself to recirculate the energy. The material challenges here shift from building a shell to moving mountains, or rather, moving stars. It would require placing neutron stars or small black holes into exacting positions, a feat of celestial engineering that redefines the word ambition. These concepts highlight a profound shift in thinking. Harvesting energy from a black hole is not about constructing a giant machine in the traditional sense. It is about becoming a cosmic gardener, learning to prune and guide the natural forces that already rage around these objects. The reactor chamber is not built, it is discovered, and the mirror is not assembled. It is cultivated from the very fabric of the spinning vortex. This moves our challenge from the realm of impossible material science into the domain of gravitational and electromagnetic mastery, a technology that feels less like engineering and more like a form of applied astrophysics. Yet, even if we solve the mirror, a deeper, more subtle question remains. What is the true cost of withdrawing this cosmic capital, and what does it do to the bank itself? The most powerful engines in the observable universe already exist, and they are powered by this very principle. While we have been discussing theoretical blueprints, nature has been running a practical demonstration for billions of years. This is the Blandford-Znajek process, a mechanism where a spinning black hole naturally converts its rotational energy into colossal jets of matter and radiation, lighting up the cosmos. It represents a shift from speculative mechanics to an electromagnetic reality, a cosmic dynamo already in operation. Here, the black hole is not a passive object to be mined, but an active participant in a grand electrical circuit. The key components are the black hole's intense spin, a strong magnetic field anchored in a surrounding accretion disk of hot plasma, and the twisted geometry of spacetime itself. The magnetic field lines are like wires frozen into the swirling plasma of the disk. As the black hole spins, it drags these embedded field lines around with it, twisting them into a tight, rotating coil. This motion, through the fundamental laws of electromagnetism, generates a powerful electric field. In the intense environment near the event horizon, This electric field becomes so strong that it rips pairs of particles and antiparticles from the quantum vacuum itself, creating a conducting plasma that fills the region. Now the circuit is complete. The black hole and its magnetic field act like a gigantic unipolar inductor, a cosmic version of a simple electrical generator. The spinning black hole is the rotor, the magnetic field is the stator, and the plasma provides the conductive path. This sets up a tremendous voltage difference between the black hole's poles and the outer parts of the accretion disk. Charged particles in the plasma are accelerated along these magnetic field lines to velocities approaching the speed of light. They are focused into two narrow, oppositely directed beams that shoot out from the black hole's poles, punching through the accretion disk and extending for thousands of light years into intergalactic space. These are the relativistic jets we observe from active galactic nuclei and quasars, some of the most energetic phenomena in the universe. The energy for these dazzling beams comes directly from the black hole's rotational spin. Each particle launched into the jet carries away a tiny bit of the black hole's angular momentum, slowly breaking its rotation. This is not a thought experiment. It is an observed astrophysical process of immense power, a natural example of black hole energy extraction on a scale that dwarfs all the stars in a galaxy combined. For a future engineer, the Blandford-Znajek process offers the most plausible large-scale model. Instead of building a fragile mirror or orchestrating particle splits, a civilization might learn to tap into this pre-existing cosmic circuit. The engineering would involve not creating the dynamo, but learning to graft onto it. One could imagine placing vast superconducting loops or magnetic collectors into the path of these natural jets, or perhaps even learning to modulate the magnetic field in the accretion disk to control the power output. The black hole becomes a steady, predictable power source, its rotational energy converted into a directed stream of high-energy particles and radiation that can be harvested. This transforms the challenge from one of fundamental physics to one of immense, but perhaps not impossible, systems engineering. It suggests that the universe has already built the reactor core for us. Our task would be to construct the turbines and the grid around it. This vision moves energy harvesting from the realm of pure theory into a domain of staggering, yet strangely familiar engineering ambition, where the power lines are magnetic fields light years long and the generator is a spinning wound in spacetime itself. The numbers behind this concept are what truly shatter our sense of scale. To move from theory to feasibility, we must ask a simple question: how much energy are we actually talking about? The answer lies in the mathematics of a maximally spinning black hole, what physicists call an extremal Kerr black hole. For such an object, up to 29% of its total mass energy is stored not in its immovable core, but in its furious rotation. This is not a small percentage. It is a reservoir of almost incomprehensible magnitude. Let us ground this with a comparison. Take our Sun. Over its entire 10 billion year lifetime, the Sun will convert only about 0.1% of its mass into energy through nuclear fusion in its core. That fusion process powers our entire solar system. A spinning black hole, however, can theoretically yield nearly 300 times more energy from its rotation alone, and from a much more concentrated source. The scale becomes truly galactic. Consider a modest supermassive black hole, one with the mass of 1 million suns. The extractable rotational energy from such an object would be equivalent to the total energy output of every star in a large galaxy, like our Milky Way, shining at their full brightness for over 100 million years. It is a stockpile of power that operates on cosmological timeframes. To frame it in human terms, our entire global civilization currently consumes energy at a rate of roughly 18 terawatts. The rotational energy from a single stellar mass black hole, one just a few times heavier than our Sun, could meet that demand for a period longer than the current age of the universe. For a supermassive black hole, the duration stretches into timescales so vast they lose all practical meaning, becoming functionally infinite from any human or even species perspective. This is the profound meaning of a black hole engine. It is not a source of literal mathematical infinity, but a well so deep that for any conceivable civilization with any conceivable ambitions, it might as well be bottomless. The physical limit exists. We could, in theory, extract that 29% and slow the black hole to a halt, rendering it a non-rotating and much less useful object. But that process, even at maximum efficiency, would take eons upon eons. For all practical purposes, it represents a bridge from an energy-scarce existence to an energy-abundant future, where power is no longer a commodity to be rationed, but a fundamental feature of the environment, as ubiquitous and reliable as gravity itself. This shifts the grand challenge from finding energy to managing the responsibility that comes with wielding a force that can reshape not just worlds, but the very structure of spacetime around them. But a reactor needs fuel, and here we encounter a profound cosmic irony. To keep the lights on with a black hole engine, you must keep feeding the beast. The most practical methods, like the natural Blandford-Znajek dynamo, do not run on the black hole's rotation alone. That spin is the battery, but the magnetic fields that tap it require a constant, charged environment to exist. They need an accretion disk, a swirling storm of superheated plasma falling into the black hole. Without this flowing river of charged matter, the magnetic fields would be weak, disorganized, or simply not there at all. The black hole would be a silent, dark spinner, its immense rotational energy locked away with no natural circuit to access it. So the fuel for our cosmic power plant is not the black hole itself, but the matter we deliberately feed into its grasp. This creates a fascinating and practical dilemma. In the pristine, idealized thought experiments, we imagine a solitary, isolated black hole in empty space. We can, in theory, extract energy from it forever using the Penrose process or superradiant scattering with a mirror, slowly draining its spin until it becomes inert. That scenario requires no additional fuel. The black hole is both the engine and the fuel tank, but it is also incredibly slow and inefficient from a human perspective, and building the containment structures for superradiance is a monumental challenge. The Blandford-Znajek process, by contrast, is nature's own high-power output model. It is fast, violent, and observable across the universe, but it demands a constant supply of matter to maintain the accretion disk and its embedded magnetic fields. You are not just harvesting the black hole's spin, you are using infalling matter as a catalyst, a kind of cosmic kindling to keep the magnetic fires burning. In this model, the black hole is the engine, but the accretion disk is the boiler. So what does a civilization do? Does it seek out a quiet, isolated black hole and attempt the slow, delicate work of pure rotational mining, a project for the ages? Or does it find an active black hole, one already feeding, and build its infrastructure around that raging storm, accepting the need to manage a perpetual fuel supply? The answer likely depends on the goals and the timeline. For a stable, long-term energy base spanning millions of years, the slow drain of an isolated black hole might be preferable. But for immense, concentrated power needs, perhaps to accelerate interstellar travel or power galaxy-spanning computations, tapping into an active galactic nucleus would be the only way to draw enough power. This turns energy harvesting into a form of cosmic resource management. You would need to locate and perhaps even engineer a steady stream of matter. This could be done by redirecting asteroids, comets, or even the slow siphon of a gas cloud from interstellar space into a controlled feed. The engineering shifts from building a mirror to building a conveyor belt on a solar system scale. It forces us to see the black hole not as a standalone machine, but as the heart of a vast and carefully managed ecosystem, one where we balance the fuel input against the power output, tending to the most powerful furnace in existence to keep our civilization alive. This power comes with a terrifying responsibility. The very forces that make a black hole engine possible are also those that could tear it apart in an instant. The primary danger is not the black hole itself, but our interaction with it. The extraction process, whether through superradiant scattering or magnetic coupling, is a delicate balance. It is like trying to siphon gasoline from a tank while the car is racing at full speed. If we draw energy too quickly or in an uncontrolled manner, we risk triggering instabilities that could vaporize our entire infrastructure. The magnetic fields in the accretion disk, for instance, are not static cables. They are chaotic, writhing structures prone to sudden reconnection events, releasing bursts of energy that could overload any collection system. A miscalculation in the Penrose process could send a fragment of matter crashing into the collector array at relativistic speeds. The engineering challenge, therefore, is not just about building big, but about building smart with an unimaginable capacity for control. We would need feedback systems of exquisite precision, monitoring the black hole's rotational state, the density of the accretion disk, and the power output in real time, and making adjustments on timescales so short they approach the limits of physics. These systems would have to operate in an environment where time itself is stretched and squeezed by gravity, where a second near the event horizon is an hour for a distant operator. The control algorithms would need to account for these relativistic effects, predicting and responding to events before they even happen from our outside perspective. It is a level of systems engineering that makes our most complex technologies look like stone tools. But beyond these operational instabilities lies a more profound, theoretical danger. The fuel for our engine is the black hole's spin. As we extract energy, we slow it down. But what if we could add spin? What if, through some error or deliberate act, we push the black hole past its theoretical maximum? General relativity provides a strict limit, the extremal limit, where a black hole's spin is as fast as it can possibly go. If it were to spin any faster, mathematics suggests its event horizon would vanish, exposing the central singularity to the outside universe. This hypothetical object is called a naked singularity. A naked singularity is not just a black hole without a cloak. It represents a breakdown in the predictable laws of physics as we understand them. The intense, infinite curvature of the singularity would no longer be hidden behind an event horizon's cosmic censorship. The consequences are purely speculative but deeply unsettling. The environment around a naked singularity could become wildly unpredictable, with causality breaking down and the normal rules of space and time no longer applying. For our power plant, pushing the black hole toward this limit would be the ultimate catastrophe. The stable, albeit violent, geometry we depend on would dissolve into chaos. The very machinery of energy extraction, reliant on the predictable warping of spacetime in the ergosphere, would become meaningless. The reactor would not just fail, it would transform into something unknowable and potentially dangerous on a fundamental level. This makes stability the paramount concern, not just for efficiency but for existential safety. The control systems must therefore have a dual purpose. They must optimize energy extraction, but they must also vigilantly guard against ever approaching the extremal limit. They would function as both throttle and governor, constantly applying a gentle brake to ensure we only ever siphon energy from a safe, stable, spinning black hole. This transforms the entire endeavor from a simple mining operation into a perpetual act of cosmic balance, a dance on the edge of a whirlpool where a single misstep could unravel the very fabric of reality around it. Even the most powerful engine in the universe must obey the fundamental rules of reality. This brings us to the ultimate limits, not of engineering, but of physics itself. How can a process that seems to extract endless energy from a single object possibly square with the unbreakable laws of thermodynamics? The answer is found not in the machinery, but in the black hole's own transformation. The first law of thermodynamics is the law of energy conservation. It states that energy cannot be created or destroyed, only transformed. Our harvesting schemes obey this law perfectly. We are not creating energy from nothing. We are converting the black hole's stored rotational energy into a form we can use, like kinetic energy in escaping fragments or radiation in amplified beams. Every single unit of energy we collect is matched by a precise decrease in the black hole's own rotational momentum. The black hole pays for our power with its spin. The second law of thermodynamics is more subtle and profound. It states that the total entropy or disorder of a closed system must always increase. At first glance, extracting clean, usable energy from a chaotic black hole seems to defy this. Aren't we creating order from chaos? The reconciliation is beautiful and inevitable. As we drain the black hole's spin, we are not decreasing the universe's total entropy. We are increasing it. A spinning black hole is a highly ordered, low-entropy object. Its rotation is a specific, organized state. When we extract that rotational energy, we slow it down. We are dispersing that concentrated order into the wider universe. The energy we collect will eventually be used, radiated as heat, and spread out, increasing the overall disorder of the cosmos. Furthermore, the black hole itself evolves. Its mass decreases slightly, and its event horizon area increases. In black hole thermodynamics, the area of the event horizon is directly proportional to its entropy. So, as we harvest energy, the black hole's entropy grows. We are trading the ordered spin for a more disordered, larger, and quieter black hole. This leads to a fundamental boundary, a point of no return in our mining operation. Physicists define something called the irreducible mass. This is the portion of a black hole's total mass that is locked away in its non-rotational, purely gravitational core. No known process, not the Penrose process, not superradiance, can extract energy from this irreducible mass. It is the ultimate ash of the cosmic fire. You can think of it like squeezing water from a sponge. You can get a lot out, but eventually, the sponge reaches a point where it is as dry as it can possibly be. That dry sponge is the black hole's irreducible mass state. All the usable rotational energy has been spent. What remains is a simple, non-spinning black hole, from which no further mechanical energy can be taken. This introduces the final guardian of cosmic order, the cosmic censorship hypothesis. This is not a law, but a deeply held conjecture in general relativity. It proposes that nature abhors a naked singularity. The gravitational collapse that forms a black hole will always wrap the central singularity in an event horizon, hiding its infinite curvature from the rest of the universe. For our purposes, cosmic censorship sets the ultimate speed limit. It prevents us from spinning a black hole so fast that its event horizon disappears, which would theoretically allow for even more energy extraction, but at the cost of unleashing unpredictable physics. The hypothesis acts as a cosmic governor, ensuring the black hole remains a stable, predictable engine with clear boundaries, rather than a runaway anomaly. So the promise of infinite energy meets its sobering, elegant limits. We are not tapping a perpetual motion machine, but a vast, one-time battery. Its energy is finite, governed by conservation, and paid for with increasing entropy. The black hole is not a magic well, but a cosmic reservoir slowly and irreversibly transformed by our use, its furious spin winding down toward a silent, irreducible end. This transformation itself points to the final, most speculative application of all, where we are not just harvesting the black hole's energy, but fundamentally altering its destiny. This elegant thermodynamic accounting, however, rests on a classical view of the universe. When we bring quantum mechanics into the picture, the very foundations of our cosmic power plant begin to shimmer with uncertainty. The smooth, predictable spacetime described by Einstein around a black hole is an illusion at the smallest scales. At the quantum level, the event horizon is not a sharp, one-way membrane. It is a seething, chaotic foam of virtual particles popping in and out of existence, a consequence of Heisenberg's uncertainty principle. This quantum froth introduces two profound complications for any serious energy harvesting operation: the information paradox and the slow, cold drip of Hawking radiation. First, consider the information paradox. In classical physics, if an object falls into a black hole, all information about its structure, its atoms, its history is lost forever behind the event horizon. It contributes only to the black hole's mass, charge, and spin. But quantum mechanics insists that information cannot be destroyed. This creates a deep conflict between our two most successful theories of reality. For our power plant, this paradox is not just philosophical. If information is somehow preserved or encoded on the horizon itself, it suggests the black hole's surface is not a simple boundary but an active, complex system. A mature harvesting station operating over millennia would not just be interacting with a gravitational whirlpool. It would be interfacing with what some physicists call the holographic surface of the black hole, where all information about everything that ever fell in is stored in a scrambled, two-dimensional form. This could have practical, if mind-bending, consequences. The process of extracting rotational energy, whether through superradiance or magnetic coupling, might subtly alter this information landscape. It is conceivable that the most efficient, long-term management of a black hole engine would require us to monitor not just its mass and spin, but the quantum state of its horizon, treating it less like a pit and more like a cosmic hard drive that must be kept in a stable, operational condition. The second quantum effect is Hawking radiation. Due to the intense gravitational field, one of a virtual particle pair can fall into the black hole while the other escapes, appearing to an outside observer as a faint thermal radiation slowly leaking from the horizon. This process causes the black hole to lose mass and eventually evaporate over astronomical timescales. For a stellar mass black hole, this evaporation would take longer than the current age of the universe. For a supermassive black hole, it is utterly negligible. So why would a harvesting civilization care about this imperceptible whisper? Because Hawking radiation represents a fundamental, irreversible energy loss mechanism that operates in parallel to our large-scale engineering. It is a tiny, constant leak in the battery we are trying to drain. More importantly, it is a purely quantum process that extracts energy from the black hole's mass itself, not its spin. This suggests a future, hyper-advanced stage of energy utilization. A civilization might first harvest the classical rotational energy via the Penrose or Blandford-Znajek processes, a massive, rapid withdrawal. Then, as the black hole slows and cools, they might transition to directly harnessing or even amplifying the quantum Hawking process, squeezing every last bit of usable energy from the fading remnant. The ultimate engine would therefore be a hybrid, blending the colossal forces of general relativity with the delicate tricks of quantum field theory. It would treat the black hole as a complete thermodynamic object, managing its spin, its temperature, and the information at its boundary in a unified framework. The control panels for such a station are impossible for us to envision, requiring a physics that seamlessly merges the very large with the very small. This quantum layer transforms our perspective once more. We are no longer just cosmic engineers building a dam in a space-time river. We are becoming stewards of a quantum gravitational system, learning to tend a fire that burns on the edge of both being and nothingness. The ultimate purpose of such an engine is to power a civilization of a scale we can barely comprehend. To understand where this technology fits in the grand story of intelligence in the cosmos, we turn to the Kardashev scale, a simple but profound way of classifying civilizations by their energy use. A Type 1 civilization has mastered all the energy available on its home planet, harnessing sunlight, wind, and geothermal flows. A Type 2 civilization has graduated to stellar engineering, capturing the total energy output of its star, perhaps by building a structure like a Dyson sphere. A Type 3 civilization is truly galactic, controlling the energy output of billions of stars across its entire galaxy. Where would a civilization that harvests black hole energy fall on this scale? The answer is both definitive and transformative. Successfully building and maintaining a black hole power plant would be the unmistakable signature of at least a Type 2 civilization, and arguably the first stable step into Type 3. It represents a shift from stellar to gravitational engineering. Instead of wrapping a single star, you are taming an object born from a star's collapse, an object whose usable energy can dwarf that star's entire lifetime output. This is not merely a bigger power source, it is a different kind of power altogether, centralized, stable on million-year timescales, and rooted in the fundamental geometry of the universe. It moves a civilization's energy base from the fusion furnaces of stars to the spinning wounds in spacetime itself. The societal implications of such a shift are staggering. With energy functionally infinite and centralized around a single titanic engine, the very concept of scarcity would dissolve for that civilization. The economic and social structures built on competition for limited resources would become relics of a distant, primitive past. The central challenge would no longer be generating power, but managing and distributing it, and deciding what to do with a universe of possibilities. Imagine the projects such limitless energy could enable. Interstellar travel would transition from perilous, generational voyages to routine commerce. A civilization could power immense light sails or even warp spacetime itself, making journeys across the galaxy feasible. Planetary and stellar engineering would become trivial. You could terraform worlds not over millennia, but over centuries, moving atmospheres and adjusting orbits with directed energy beams. You could halt the death of a star by feeding it additional matter, or sculpt nebulae into new structures. The black hole engine becomes the ultimate tool, its energy directed by a civilization's will. This concentration of power also suggests a profound structural change. A civilization powered by a single, colossal source might become intensely centralized, with all its infrastructure and population orbiting the cosmic dynamo. Or through the mastery of beaming energy across light years, it might become a diffuse, galaxy-spanning network, all connected back to the central black hole as a power grid connects to a main plant. The black hole would become the heart of their civilization, both physically and culturally, a permanent fixture in their mythology and science. It represents a final, mature step in a species' relationship with its environment. They are no longer inhabitants of a world or even a solar system. They are stewards of a gravitational engine, their destiny forever intertwined with the slow spin of a dark giant. This vision forces us to ask a deeper question about our own future. Is the drive to harness such overwhelming power an inevitable milestone for any intelligent species, or is it a choice that defines the very soul of a civilization? Finding the perfect black hole for our engine is the first and perhaps greatest practical hurdle. Our galaxy is thought to contain hundreds of millions of stellar mass black holes, the remnants of massive stars that have ended their lives. But most of them are terrible candidates. They are often locked in binary systems whirling around a companion star, pulling streams of matter from it in a violent, unpredictable dance. This chaotic environment is the opposite of the stable, controlled reactor core we need. An active accretion disk is useful, but one fed by a stellar companion is like trying to build a hydroelectric dam in the middle of a hurricane. The system is too volatile, the energy flows too erratic. We need a solitary black hole, one drifting in the quiet darkness between the stars, with no close companions to disturb its geometry. Locating such an isolated object is a monumental challenge in itself. Black holes are, by their nature, invisible. We infer their presence by the gravitational influence they exert on nearby light or passing stars. A truly isolated black hole with nothing nearby to influence is a ghost in the cosmic night. Our current surveys might simply miss it. So the first phase of this project would involve a galactic-scale search, using the most sensitive gravitational wave detectors and astrometric telescopes, looking for the subtle lensing of distant starlight or the faint, telltale wobble of a solitary star being tugged by an unseen companion. It is a search for a needle in a galaxy-sized haystack, requiring patience and technology far beyond our own. Assuming we find a suitable candidate, the next challenge is even more daunting. What if the perfect black hole is in the wrong neighborhood? The energy required to move a stellar mass black hole, even a small distance, is beyond comprehension. You cannot push it with a rocket. Its gravity would swallow any physical thruster. The only conceivable method would be to use gravity itself as a tow cable. You could attempt to maneuver a series of massive objects, like neutron stars or other black holes, into precise orbits around it, using their gravitational pulls to nudge it slowly over millennia. The energy investment for such a celestial game of billiards would likely dwarf any energy we could hope to harvest from the black hole itself for millions of years. It is an exercise in cosmic absurdity. Alternatively, could we create our own? The idea of artificially creating a black hole, perhaps by compressing matter in an advanced particle collider or through some unimaginable concentration of energy, is a staple of speculative fiction. But the scales are prohibitive. To create even a tiny micro-black hole would require energies quintillions of times greater than our most powerful particle accelerators, concentrating the mass energy of a mountain into a space smaller than an atom. And that microscopic black hole would evaporate via Hawking radiation in a fraction of a second, useless for our purposes. To create a stable, stellar mass black hole artificially, you would essentially need to replicate the death of a massive star, a process that naturally releases more energy than a galaxy emits in a year. The idea shifts from engineering to a kind of controlled stellar catastrophe, a power source that costs a supernova to build. This stark reality forces a much more plausible, yet still staggering, conclusion. We do not find the perfect black hole, and we certainly do not move or build one. We adapt to the universe as we find it. The only feasible path is to build our civilization's infrastructure around an existing black hole that meets most of our criteria. This means our search changes. Instead of seeking a mythical, perfectly isolated specimen, we look for the best available site. We might choose a quiet stellar mass black hole at the edge of a globular cluster where stellar densities are lower. Or for truly astronomical power needs, we might set our sights on the ultimate prize, the supermassive black hole at the galactic center. These giants, like Sagittarius, a star at the heart of the Milky Way, are already surrounded by complex environments of gas, stars, and magnetic fields. They are not pristine, but they are stable on million-year timescales. The engineering challenge then transforms completely. It is no longer about creating the reactor core, but about constructing a metropolis in the most hostile environment in the galaxy. We become cosmic city planners, designing habitats, energy conduits, and control systems that can withstand the titanic forces, the intense radiation, and the twisted spacetime orbiting a gravitational leviathan. The black hole chooses the address. Our ingenuity determines what we can build there. The sheer scale of this engineering project defies any human analogy. Building around a black hole is not like constructing a power plant on Earth, or even a Dyson sphere around a star. It is architecture on a galactic stage, where the blueprints are drawn in light years and the building materials are forces of nature. The most plausible design would not be a single, rigid structure. The gravitational tides near a black hole are so fierce they would spaghettify any solid object, stretching it into a stream of particles before it could even complete a single orbit. Instead, the infrastructure must be fluid, dynamic, and distributed. Picture not a solid shell, but a vast, intelligent swarm. Imagine billions upon billions of individual energy collectors, each one a sophisticated spacecraft or satellite, orbiting in a dense, coordinated cloud around the black hole's equatorial plane. This is a Dyson swarm, but one built not to capture starlight, but to harvest the amplified radiation, particle jets, and twisted spacetime of a Kerr black hole. Each collector would be autonomously guided, constantly adjusting its position with minute thruster bursts to maintain a stable orbit in the chaotic gravitational field, all while beaming the harvested energy to a central processing station or out to distant colonies. The swarm itself would be a shimmering, metallic nebula, a hive of activity dancing on the edge of the ergosphere's fury, but collectors are only one piece. To truly tap the magnetic dynamo of a Blandford-Znajek process, you need to interact with the black hole's magnetic field. This suggests another layer of infrastructure, one made of pure force. Envision superconducting loops of unimaginable size, perhaps constructed from captured asteroids spun into cables and charged into electromagnets. These loops would be placed in strategic orbits to shape and reinforce the black hole's natural magnetic field, channeling the relativistic jets into more focused, manageable beams for collection. Some theoretical designs speak of a Penrose ring, a torus of material or energy that orbits within the ergosphere itself, designed to catalyze the particle splitting process on an industrial scale. These would not be rings of metal, but contain plasma storms or directed energy barriers, structures that exist more as persistent events than as solid objects. The common thread is that all of this presumed technology operates at the absolute limit of material science. Consider the environment. Near the ergosphere, space is flooded with lethal radiation, from high-energy X-rays to gamma rays. Temperatures in the accretion disk can reach millions of degrees. Cosmic rays and particles accelerated to near light speed pepper everything. Any physical component must withstand this relentless bombardment for centuries or millennia. Our strongest alloys, our most advanced ceramics, would vaporize in an instant. The collectors and coils would need to be built from materials we can scarcely conceive, perhaps engineered at the atomic level using forces we do not yet understand, or constructed from the very space-time fabric itself, using controlled gravitational or magnetic fields as their primary structural support. They would be less like machines and more like solidified physics, artifacts of a civilization that has learned to weave the laws of the universe into tangible form. This contrast between the staggering, beautiful concept and the brutal, unforgiving reality is the central paradox of black hole engineering. The vision is one of sublime cosmic mastery, a civilization bending a titan to its will. The practical reality is a desperate struggle against the most destructive forces in existence, a battle fought not with strength but with perfect, unyielding precision. It asks whether intelligence, in its ultimate form, is defined not by conquering nature, but by learning to build with its most violent storms. This fundamental disconnect in the flow of time would be the most profound challenge for any operators of a black hole power plant. Near the event horizon, the gravitational pull is so intense that it warps time itself, a phenomenon called gravitational time dilation. For a control station or habitat orbiting close to the black hole, perhaps to manage the delicate magnetic coils or the swarm of collectors, time would pass far more slowly than it does in the distant universe. A single hour of work for an engineer on that station could equate to years, decades, or even centuries passing for the civilization that sent them. This creates an impossible scenario for real-time command and control. You could not have a mission controller on a distant planet giving live instructions. By the time their signal saying "adjust the field strength" reached the station near the horizon, years would have passed in the outside world, and the crisis they were responding to would be ancient history from the station's perspective. The feedback loop of information would be shattered. This forces a radical rethinking of what operation even means. One solution is the complete removal of biological operators from the immediate vicinity. The inner sanctum of the reactor, the space within the intense time dilation field, would have to be run by artificial intelligence, not just any AI, but systems endowed with complete autonomy. They would need to monitor the chaotic physics of the ergosphere, manage energy extraction, and perform repairs, all based on pre-programmed goals and the ability to make independent, real-time decisions that could affect the power output for centuries of external time. These AI custodians would operate in a strange temporal isolation, their swift computational cycles ticking away while the outside galaxy aged around them. For the civilization that built them, checking in on these AI guardians would be like archaeologists studying a monument from a bygone era, receiving status reports that were compiled generations ago. The alternative is a conscious, chilling acceptance of the time differential as the cost of doing business. A society might choose to staff the inner stations with volunteers who understand they are stepping out of the main flow of cosmic history. These operators would live their entire lives, raise families, and build cultures in the stretched time near the black hole, knowing that with each orbit, their home civilization far away leaps forward into a future they can never rejoin. Communication with the outside would be a one-way stream into the past, a series of historical dispatches. This creates a unique, poignant form of isolation, where the keepers of the flame become living relics, guardians of a machine whose ultimate purpose unfolds in a time frame they cannot witness. The very act of tending the engine would be an act of profound sacrifice, a commitment not to a lifetime of service, but to an epoch. It transforms the power plant from a mere engineering project into a deeply philosophical undertaking, questioning the nature of time, legacy, and what we are willing to trade for the promise of near-infinite power. The black hole's spin is not the only key that can unlock its energy vault. Theoretical physics offers other, even more exotic models, each with its own unique blueprint for a cosmic power plant. Consider the charged black hole described by the Reissner-Nordström solution. This is a black hole that possesses not just mass and spin, but also a significant electric charge. The intense electric field surrounding such an object creates a second region of interest, an electrostatic equivalent to the ergosphere. Here, the interplay between gravity and electromagnetism could, in principle, allow for energy extraction processes analogous to the Penrose mechanism, but powered by charge instead of rotation. An object with the right electrical properties could enter this zone, split, and allow one fragment carrying negative energy to fall in, while the other escapes with amplified energy, effectively draining the black hole's charge. This model presents a fascinating alternative, a different flavor of the same fundamental physics, where the fuel is electromagnetic potential rather than angular momentum. Yet, in our observed universe, charged black holes are likely rare. Space is an excellent conductor, and any significant net charge on a black hole would quickly be neutralized by attracting opposite charges from the surrounding plasma. The spinning black hole remains the more robust and naturally occurring candidate for our engineering dreams. But what if our understanding of the cosmos is incomplete? The most speculative frontiers of physics suggest that the three dimensions of space we experience might not be the whole story. Theories like string theory propose the existence of extra, compactified dimensions, curled up at scales far smaller than an atom. In such a universe, a black hole would not be a simple four-dimensional object. It could be a higher-dimensional entity, a brain, or a stringy remnant with properties utterly alien to our classical models. Could these hidden dimensions offer new pathways for energy extraction? it is a tantalizing possibility. The geometry of a higher dimensional black hole might permit different types of rotational states or vibrational modes in the extra dimensions, each representing a reservoir of energy we cannot currently perceive. The process of harvesting might involve exciting these hidden degrees of freedom, tapping into energies that literally exist in directions we cannot point to. The mechanisms are purely mathematical conjectures, but they hint at a universe where the ultimate power sources are not just immense, but multidimensional. A civilization mastering such physics would not see a black hole as a dark sphere, but as a complex, vibrating knot of spacetime with energy channels flowing through every folded dimension. This shifts the goal from building a bigger engine to developing a deeper perception, a way of seeing and interacting with the full, hidden architecture of reality. The promise is no longer just infinite energy, but a complete rewriting of the cosmic rulebook on how energy can exist and be moved. Yet with such power comes a responsibility that echoes across the cosmos. The ability to shape a black hole's energy output is, by definition, the ability to shape reality on a stellar scale. This introduces a suite of ethical and existential risks that any civilization must confront long before the first collector is deployed. The most immediate danger is not to the engineers but to the galactic neighborhood. A black hole engine, especially one tapping an active accretion disk, is not a subtle device. The relativistic jets and amplified radiation it produces are inherently directional and incredibly powerful. A miscalibration or even a routine adjustment could inadvertently sweep a jet across a nearby star system. The consequences would be catastrophic, sterilizing planets and disrupting the delicate balance of any life within its path. Operating such a device requires a level of foresight and cosmic stewardship we can scarcely fathom. A permanent awareness that a mistake is not measured in dollars or downtime, but in light years of unintended consequence. This leads to the darker, inevitable question of weaponization. In the wrong hands, a controlled black hole is not an engine, but the ultimate cannon. The directed energy from a focused jet could be repurposed, its unimaginable power turned not toward creation, but toward destruction. The scale of such a weapon is beyond any conventional arms race. It would be a tool of absolute deterrence or of absolute domination, capable of threatening not just worlds but entire stellar clusters. The mere existence of this technology would force a civilization to grapple with profound questions of governance, security, and the very nature of power. Could any single society be trusted with the keys to a galactic furnace? The development of this technology might itself become the greatest filter, a test of whether a species can mature ethically in step with its technological prowess, or whether it will inevitably turn its greatest tools into instruments of control. Beyond these external threats lies an internal, more subtle existential risk, the danger of a cascading engineering failure. We are not simply building a dam. We are interacting with an object whose stability is governed by the deepest laws of physics. A major error in the energy extraction process could, in theory, trigger a runaway instability. Imagine a feedback loop in the magnetic containment or a critical overload in the superradiant scattering process. Instead of a controlled bleed of energy, the system could go into a violent, uncontrolled release. At its most extreme, such a failure could theoretically push the black hole's geometry past a point of no return, potentially exposing a naked singularity. While this remains a highly speculative outcome, it underscores the stakes. We are not just risking a meltdown, we are risking a fundamental alteration of local spacetime, an event whose full consequences are unknown but could render an entire region of the galaxy unpredictable or uninhabitable. We must weigh these staggering risks against the promised benefits of near-limitless energy. The argument for proceeding hinges on the idea that such power could elevate a civilization beyond scarcity. ending conflicts over resources and enabling projects of cosmic benevolence, from halting stellar deaths to seeding life across the galaxy. It represents a leap from a species surviving within its environment to one actively nurturing its cosmic home. Yet this optimistic view assumes a unified, wise, and stable civilization. History suggests that power of this magnitude is just as likely to cement tyranny as it is to foster utopia. The black hole engine, therefore, is more than a technological milestone. It is a mirror. It forces a species to ask not can we build it, but who will we become if we do. The decision to harness a spinning giant may be the final exam for any intelligent life, testing whether its wisdom can finally catch up to its wonder. Theoretical physics often finds its purest expression not in academic journals, but in the stories we tell. The idea of harvesting energy from a spinning black hole has ignited imaginations for decades, becoming a powerful narrative engine in science fiction. These stories serve as a vital cultural bridge, translating complex equations into compelling human drama and bringing these cosmic concepts to a global audience. Consider the film Interstellar. While its primary focus was on time dilation and love transcending dimensions, the fictional beings behind the wormhole had mastered gravitational manipulation on a scale that hints at such advanced energy use. The film visualized the warping of spacetime around the black hole Gargantua with unprecedented scientific accuracy, thanks to physicist Kip Thorne's involvement. This gave millions of viewers an intuitive, visceral feel for the twisted geometry we have been discussing, making the ergosphere and frame dragging feel less like abstract math and more like a tangible, if terrifying, landscape. Across countless novels and galactic empire tales, the trope of a civilization powered by a central, mysterious energy source is a recurring theme. Often, this source is a black hole or a similar cosmic anomaly. These narratives take the theoretical principles of the Penrose process or Blandford-Znajek mechanism and simplify them into a plot device, a silent, spinning heart that powers faster than light travel, planetary shields, or city-spanning force fields. The technical details are streamlined for pacing and character, but the core wonder remains the gravitational dynamo, a testament to humanity's enduring fascination with tapping the universe's ultimate forces. This dramatization is not a flaw but a feature. It acts as a gateway, sparking curiosity in a viewer or reader who might never pick up a textbook on general relativity. A thrilling scene of a starship diving into an ergosphere to escape pursuers plants a seed of question. Is that even possible? What would really happen? That moment of curiosity can be the first step toward a deeper understanding of the actual physics. These stories also explore the profound societal and ethical questions we touched upon earlier, but through the lens of human conflict and emotion. They ask, what does it do to a culture to build its identity around such a power source? Does it create a stable utopia or a rigid, controlling hegemony? Narratives often depict the catastrophic failure of such a system, the black hole bomb scenario playing out as a galaxy-ending threat. This narrative exploration serves as a kind of collective thought experiment, allowing us to grapple with the consequences of technologies we may never build. Science fiction, therefore, performs a dual function. It inspires new generations of scientists and engineers by painting a picture of a future shaped by deep physical understanding, and it prepares the broader public consciousness for the philosophical implications of such advancements. It reminds us that the equations of Kerr and Penrose are not just descriptions of reality, but potential chapters in our own ongoing story. A story where the line between tomorrow's science and today's fiction is perpetually and excitingly blurred. From a physicist's elegant thought to the foundation of a galactic empire, the journey of black hole energy is a story of ideas straining against reality. We began with Penrose's simple yet profound notion, a mathematical trick where an object could steal spin from a cosmic whirlpool. That idea grew into the violent natural dynamos of quasars, the speculative mirrors of superradiant reactors, and the ultimate ethical quandaries of wielding such power. The physics, in its purest theoretical form, permits it. The equations of general relativity contain no clause forbidding the extraction of rotational energy. Yet this permission slip from the universe is written in a language of almost comical understatement. The leap from those clean lines on a page to a functioning power grid orbiting a supermassive black hole is not merely a challenge of scale. It is a chasm that redefines the very meaning of the word impossible. We are not talking about building something bigger than anything before. We are talking about engineering with forces that shred matter, in an environment where time itself becomes a variable to be managed, using materials that must be conjured from a future physics we do not yet possess. The control systems alone, operating across light years and relativistic time warps, demand a mastery over reality that feels less like technology and more like a form of natural law itself. This staggering gap between principle and practice is precisely why such thought experiments are priceless. They are not blueprints for tomorrow's construction projects. They are the ultimate stress tests for our understanding of the cosmos. By pushing an idea to its absolute limit, by asking if we can power a civilization from a spinning singularity, we probe the deepest foundations of our theories. We force general relativity to confront quantum mechanics at the event horizon. We watch thermodynamics play out on a stage where entropy is measured by the area of a black hole. We discover whether our mathematical descriptions of spacetime hold up under the most extreme interrogation we can devise. In doing so, we learn far more about the universe and about the limits of our own knowledge than we ever would by studying only the possible. The true value of this exercise may not be the vision of infinite energy, but the clearer map it gives us of the boundaries of physics itself. So the next time you hear of an idea that sounds like pure science fiction, a concept that bends the mind and seems utterly beyond reach, remember the spinning black hole. Remember that within the silent language of mathematics, other impossibilities are waiting. What other universe-altering technologies might be hiding, not in our workshops, but in the elegant scribbles of a theoretical physicist's equation?